Hey David, and thanks for making this call.
Hey, you bet, Phil. Good to see you again.
Yeah, good to see you. First little funny story. We were trying to do this online video call recording. I tried lots of stuff, and then of course David, given who he is, just snapped some fingers, and then some magical people made it all happen using some pretty awesome technology. So, David, what do you do, and how'd you get there?
Um, so I'm the chief architect at Cisco, and the story how I got here is actually quite. Um, it's probably longer than it is interesting, to be honest. But nonetheless, I started off in grad school back at the University of Minnesota in the mid '90s, and I was working on a project directing a research center trying to prove that a cluster of workstations around the University of Minnesota connected over a high-speed network could outcompete and outcompute supercomputers. And so what was interesting about this is that we ended up building and deploying the world's first production ATM network amongst a bunch of Sun and SGI workstations. I know most people on this call probably have only heard about those companies perhaps in the annals of history or in some dusty textbook, but nonetheless, we proved, in fact, given the right experiment, that we could um, outcompute a supercomputer. But the problem was to be able to prove this, we needed to connect supercomputers together. So to do that, we built the first production wide area network ATM network to connect Pittsburgh supercomputer, Minnesota, San Diego, all the big ones together. But then there was a small problem. And once we built this out, and this high speed network was called VBNS. Again, one of the very first big WAN networks. But the problem was is that supercomputers spoke to each other over this protocol called HIPPE, high performance parallel interface. And there weren't a whole lot of HIPPE interfaces available for supercomputers, so we had to invent a HIPPE switch. And then we, with a group of folks at a startup, invented HIPPE over ATM. Now, what was really interesting about this, Phil, actually, from an engineering point of view, is that a HIPPE packet in those days was 2 gigs, and an ATM cell with 53 bytes.
Yeah, yeah, yeah.
And across the wide area network, when you dropped 53 bytes, here comes 2 gigs again. And so we learned a whole lot about how to build extremely good wide area network packet generators. But as I moved forward, I found out, in my experiment, in my work, that we also needed to upgrade the Midwest University Network, which was called CICnet, and how the University of Minnesota was connected to the internet, which was NSFnet in those days. And so we started working and upgraded Minnesota's connection to NSFnet. And again, this is all pre-commercial internet, which again are down in the annals of history. So we had to do an upgrade of that wide area network. And towards this end, we started building again more WAN interfaces and more high-speed LAN pieces. And then I found, scratching my head, wow, the PhD I was getting in physical organic chemistry, that's hard. And this networking stuff is kind of easier, and it's really kind of cool. And while doing all this high speed networking, I actually met the woman who became my wife. So I'm like, wow, you can pick up girls too. This is all working out for me pretty well. So then I went to a startup that was building these HIPPE switches and we thought we had a great business plan. We are going to network all of the supercomputers on the planet. There was one small problem with this business plan. One was that you only need one switch to connect like all of NASA Goddard, all of these massive supercomputers. You only need one switch. Second business problem, if it wasn't volume, it was that a supercomputer goes for $35 million or some ungodly number of tens of millions of dollars, and a switch goes for about $350,000. And we sold 12 of them. And so we're like, oh man, that didn't quite work out. But wait a minute, there's this whole like internet thing going on over here that looks kind of popular. The internet had just gone commercial out of NSFnet, and we had built this distributed processing or distributed forwarding switch thing that, again, had the first FPGAs and then the first ASICs to build out these distributed line cards. And wait a minute, and we had a Unix machine controlling this, where the Unix machine was actually running BSD, an open source operating system that was really popular at the time. And we were using open source tools and routing tools like GateD, which most folks don't use now, but nonetheless was super popular then and actually ran NSFnet. And so we built a Unix machine on top of this cage of ASICs and FPGAs built the first world's first distributed forwarding router at that time.
Oh.
Then what ended up kind of happening was that, wait a minute, this thing actually works really, really kind of well and is really fast and has a much different scaling property than other centralized switches at the time or centralized routers at the time. And that startup ended up getting sold to a company called Ascend Communications, which back in the day was the world's biggest ISDN modem builder, which everyone had in their homes at the time. You know, upgrading from those old dial-up modems and stuff, they went to ISDN, and then they went on to cable and other technologies, of course, as well. But nonetheless, I left Ascend and went to a small startup that Cisco acquired in 1999, and I've been designing systems and ASICs and operating systems for quite a while. But one thing I just wanted to mention about that bit of history was that when I was doing my PhD work and I was working on this cluster of high performance servers connected to a high-speed networking, my real work was in parallel programming and parallel processing and operating systems, and built out parallel virtual machine, which was, using IPCs and RPCs across a high-speed network and with different QoS levels for the different types of messages. And so I was a major league OS head, and it really was. Yeah, I know. Well, back in the day, it was cool, and no offense to my other friends over there in Stanford, but what ended up coming out of this was a deep understanding for multi-threading, modular operating systems, and that in turn, with the systems experience I had building chips and systems like I just described, when I showed up at Cisco in 1999, or December 20th, 1999, in fact, at 8 a.m. over in the big executive office, they handed me a pen and they said, okay, tell us what the next router is going to be. And from there, it's just been a great opportunity to explore the different design patterns that I've learned about and that I truly believe in, and turn that into a lot of equipment that is now running on the internet.
Cool, yeah. Well, it's funny you said about the chemistry is hard and stuff, but writing code is fun. So David Navier, who's faculty here, once said he started as a math major, and he said, math is kind of hard, but writing programs are fun, right? So that's when I ended up going into computer science. Cool, and so you did a lot of work on a bunch of Cisco's major routers. Do you want to just mention a little bit about that, or?
Sure. So I was the designer of and chief architect of iOS XR, which is the current multi-chassis parallel programming modular operating system running on the service provider line, but also was the co-architect of the CRS-1, which then turned into the CRS-3, which then turned into the CRS-10 as we advanced ASIC designs. Have designed and helped do the functional design of probably on the order of about 60 ASICs now. Also worked on the ASR 9K, the ASR 1000, most of the optical kit that we sell, as I was very much into optics and physics in the day, and incorporating in particular optical processing and routers themselves, and taking the transponder shelves, which are such a huge cost of building the internet, and building those effectively directly into routers to reduce cost. From there, and all the while, even back at Ascend and doing things at the university, you have to realize that the NSFNet community and regional meetings turned into the North American Network Operators Group. And so I was...
Nano. Yeah.
Yeah, Nano. So I had to be deeply involved in there. And then as we were building out NSFNet and then building out the internet with all the providers when it went commercial, we needed a lot of protocol extensions to be able to peer with each other and build out services, and came up with effectively the current network architecture of the internet, which includes exchange points and how to do regional peering and how to do settlement-free peering. And frankly, we invented all the protocols of now what we know of being BGP, OSPF, ISIS, multicast, MPLS, etc., to fundamentally solve some of the problems that we were facing on the internet. When you couldn't get circuits delivered fast enough and you had constrained bandwidth on your link, you needed to be able to reserve bandwidth and have traffic engineering. Here comes MPLS. When you want to connect businesses in their own address space, it's really, really hard to have overlapping address space and do the correct IP routing. And well, voila, here come layer 3 VPNs. And so it was a lot of invention by necessity at the time, and just having a ton of fun, not only, of course, writing the code, defining the specs, but watching it all get deployed really, really fast. And so it was a ton of fun. And it still is a ton of fun. I'm still cranking away on new stuff. You know, I work with a lot of folks there at Stanford and helped get OpenFlow out of Gates 104 and build up the ONF, and now really focusing a lot out of the embedded OSs and focusing at controller layers, orchestration, network function virtualization, and trying to tie together server, storage, switching, and routing, and get more services on the internet. I mean, basically, Phil, my red and white blood cells are completely packetized in IP packets at this point.
I never thought about our blood being packetized, but actually Martin Casado came and gave a guest lecture in the class, talk about SDN, present the whole sort of SDN vision of having controllers and this global graph which you can operate on to then push out to the switches, and sort of that separation of control logic and forwarding logic. And so I think a lot of what you said will make sense actually to a bunch of the students in this class. They're pretty excited about the SDN stuff.
Well, I have a slightly different view maybe than Martin, and certainly when he was working at Stanford, is that having a centralized view of the topology is a great augmentation of the current dynamically routed system. And if you don't mind me to opine just for a little bit second, just on this philosophic point, a distributively routed autonomous acting set of routers forming the internet, in my opinion, does provide the fastest protection and restoration for topology failures. Now, when we started out, or the forefathers before me, the internet started up, they were worried about, frankly, thermonuclear war. And they wanted to have a consistent communication platform that no matter what happened to any city or any node, the network could stay up. Well, this translates into modern time. Hopefully, we don't have to worry about that problem anymore. But what we do have to worry about are backhoes and other real problems of things in our transmission network, which, as far as the network is concerned, they can't tell the difference what caused a fiber cut, whether it's a backhoe or you know, whatever it is, somebody with a forklift in a data center. So I still firmly believe in the tenets and power of a distributively routed network, and we can get into this more in just a second. But I really find polar conversations that everything is distributively routed or everything is centrally managed as really something best left for the bar. It's not an interesting conversation for me. And it's not an interesting conversation because when you build and deploy transport networks or ATM networks or frame relay networks or even X25 networks, if I really want to date myself, you do this with a centralized planner. And what you get to see is you get to see across summarization boundaries. And to scale the internet, we've got summarization boundaries of IP addressing all over the place between autonomous systems, whether it's Comcast, AT&T, or wherever you are in the world between those big providers. But also within those networks, there are multiple autonomous systems. And within those autonomous systems, there's multiple areas like OSPF areas. And frankly, those are the definitions of IP address summarization. Now, all that's cool. Scaling is great. We all love a bigger, better internet. But if I wanted to build a tunnel between me and you using MPLS or using anything, and I can't see your IP address because it's been summarized into a larger block, man, we spent years inventing 42 different ways to leak prefixes and do all this fancy stuff in protocols. When what's the answer? Have a logically centralized view of the entire topology. And if I want to build a path between Dave and Phil, I see your address and your topology behind your area boundary and your summarization boundary, and I can see mine over on this side, and voila, I can build an end-to-end path with quality of service, et cetera, et cetera. And that augmentation of a centralized SDN controller or a centralized controller in addition to a dynamically routed network is something that I'm really focusing on. And frankly, it might be an expected conversation you might expect to have with a guy like me, given that I kind of came out of that world, but I also came out of the world where trying to do everything centralized for ATM or frame, and I was building or we were building permanent virtual circuits all across the planet. I watched the scaling properties of that just explode. And when you're trying to deal with not just tens of thousands, but millions of potential circuits or slices, you know, in current parlance, because you know, circuits are bad and now slices are good. The scaling properties to scale to internet size stuff is really something that has to be well understood. And that's what dynamic routing and topology exchange is really, really good at. It's just really, really bad at seeing across those summarization boundaries. So the two together are just rock and roll. You know, there's no disco involved in that one. They're just cranking away.
Cool. Well, so we talk a lot about the past and kind of maybe some of the things with SDN that's happening now, but what are the things that you're most excited about that's going on in routing and sort of the wide area in the internet today? I know for a little while you were working on securing BGP. Is that work still going on, or I mean, what are you doing now?
So I am still working on securing BGP, but that's turned into a political quagmire of who's going to hold the certificate. Yeah, I mean, and is it the Department of Commerce, which actually has this thing called the IANA function, which holds all the roots of, all of our naming and numbering. I mean, it's just a political nightmare internationally and nationally, because nobody can figure out, frankly, I'll summarize it this way, Phil, nobody can figure out who's going to make money off it. And I'm not interested in solving that problem, because that problem is outside, commercial space. Somebody needs to hold the root. Somebody needs to handle all the addressing. Somebody needs to handle all the certificates associated with BGP routes. And I continue to work on this with the FCC and other governmental organizations, whether it's the EU or others, and the regional registries. But it didn't make enough progress. It didn't go fast enough for me to get through these issues. So instead, what I wanted to talk to you about today of things that are extremely cool going on the internet, especially if you ask me, have to do with a technology called segment routing. And what's different about this, and my goal with this technology, and our goal, the group of folks who are working on it, including lots and lots of providers, is to simplify MPLS networking, traffic engineering, and VPN services by actually removing protocols. And the reason why this is a bit of a shocker is that, look, I've spent decades of my career actually extending and advancing these protocols. So you'd think that I might be a guy who would just hold on to them religiously, like, this is a hammer, everything is a nail, let me go find more nails, or at least things that look close enough like nails that I can go beat them. But in fact, what's really interesting is that when you take a look at traffic engineering and wide area networking, the operational overhead and the complexity of it is in fact a major league problem. And the part of the problem is that we require the network to hold state. So when I set up an RSVP traffic engineered tunnel, I use RSVP, hence the name, but I use RSVP, which signals hop by hop through the entire network. I'd like to reserve a gig. I'd like to reserve a gig. I'd like to reserve a gig. When everybody says there's a gig, and make up your favorite number if you want more bandwidth, then you get go, start sending traffic. And every device in this path holds that state. And so then we were running into issues that, well, how many midpoint labels can you hold and how much state can you hold? And then we invented protocols that didn't require that kind of state, and they were called the label distribution protocol, where we'd say, hey, here are all the labels I'm advertising. And in another protocol, we'd say, like OSPF or ISIS, we'd say, here are all the next tops that you're supposed to bind them to. And we built a stateless MPLS network out of that. But the problem was, labels and traffic engineered tunnels those tunnels were only following best path routing. Well, what about all those other paths out there that aren't passing my traffic? What am I going to do now? I've got all this bandwidth deployed in the network. I'd really like to use it. Oh, and as a matter of fact, what if I would like to also use equal cost multipath? And when you take a look philosophically at if you want to think of it that way, philosophically at how MPLS networks are built, the notion that there are link aggregation groups at L2, like multiple Ethernet interfaces in between routers, or at equal cost multipath, which is multiple layer 3 connectivity between routers, best of luck trying to balance out your traffic across those equal cost multipath links. One, because they've been summarized in your IGP and you can actually see all those multiple adjacencies. And two, how are you going to organize a hashing algorithm network-wide across lots and lots of boxes of different eras and different vendors and different ASICs and all the rest of it? And so MPLS, I would say right now, fundamentally doesn't solve one of the major tenets of the way the internet's built, which is equal cost multipath, adding lots and lots of bandwidth between two routers. For example, if you need 400 gigs of bandwidth between two routers, let's say between Boston and New York, you can use 40 10 gig interfaces or 400 gig interfaces or whatever the case is. Now, how do I balance traffic across those? That's the problem that I'm trying to solve. So what segment routing does is, let's not use RSVP and hold all that state. Let's not use LDP and try and match up and only use best path routing. Instead, when I pass the IP address of a router, and I pass the IP addresses of all the interfaces off the router in OSPF and flood that information between all the other routers, so that way we know, quote, the topology of the network and all the adjacencies, I'm already passing, here's the interface, here's the adjacency, and here's the IP address. Well, what if I also just snuck in, what's 4 bytes between friends? What if I snuck in a label in there too? I fundamentally haven't added really a whole lot of traffic to the control plane, obviously. It's literally individual megs of RAM on a router versus the hundreds of megs of RAM or gigs of RAM required to hold the state for RSVP tunnels. So let me back up, Phil. What I've done is I've now flooded IP addresses for all the routers, IP addresses for all the interfaces and adjacencies, and I've flooded a label for everything. So now I've flooded a complete link state topology, including IP connectivity and label connectivity. And what I do differently, and here's how SDN becomes involved, what I do differently is instead of sending what would be called an explicit route object to the head end to trigger RSVP-TE, which says, I want to follow this route, this link to that router, and that link to that router, and that link to that router. That's the explicit route object that defines that. I instead program the head end with a label stack. And that label stack, I've already learned from the network. I've allocated to every device, and voila, I can use, just by programming the head end label stack, a complete path through the network utilizing equal cost multipath, using protection restoration. And I think this is, although not being discussed at the usual SDN places and not being discussed maybe lots and lots within academia yet, this is without a doubt perhaps the biggest revolution to happen in routing and routing protocols since MPLS was invented, simply because it solves some fundamental architectural problems of equal cost multipath, but it preserves fast reroute, traffic engineering, and it does it all SDN-esque, but instead of passing down, say, a classifier, you're passing down a label stack. Easy peasy. And so what I've been working on is, of course, pardon me, how to link this up into RSVP networks, how to link this up within LDP-based networks or labeled BGP networks. And what this allows me to do, and the way I'd like folks to think about it, and you to think about it, when I combine dynamically routing networks with a centralized view of the topology and a full known explicit path of labels through the network programming that head and label stack, this technology fundamentally would be called a soft permanent virtual circuit in ATM or frame terms. It's a soft PVC. Program the head ends and let signaling figure out the path in between. And believe it or not,
so it's interesting. Now we're going to I mean, we have underlying this packet mechanisms underneath, but just for needs of, I mean, core ISPs and traffic engineering and all of this the stuff in the middle, we want to go to soft circuit.
Well, let's face it. What we should have remembered that the most popular feature of those technologies was in fact soft PVCs, and we never invented it for IP-MPLS. It was a huge gaping hole, in my opinion. Instead, we jumped all the way to switch virtual circuits, which was full topology awareness of everybody at the head end. Now, Phil, the other thing I wanted to mention, and this is again a philosophical point, is that it's a different point about SDN and the requirement for logically centralized control than others make, but I think it's just because it hasn't entered the conversation on the internet yet, which is that today's IP-MPLS networks do load design via head-end only views of the topology. And so by doing head-end load...
Can you explain what that means? I'm not sure every student will quite get what that means.
Yeah, so what that means is when I want to build a path between me and you, and I want to understand how can I fit 10 gig circuit or a 10 gig tunnel between me and you, I have no idea about the load on the rest of the network. I have no idea of the load that any other entry point into the network would be putting onto the network. All I know is what I see. And all I see is a set of the topology. I don't know the utilization. I only know the reserved bandwidth. What if I don't care about the reserved bandwidth? What if I actually just want to know where can I place 10 gigs of load on the network? You can't do this from a head-end based approach. And all of MPLS and all of IP is based upon the head end having full information about the network on how to place loads.
So by the head end, you mean the person who's initiating the tunnel, basically saying, I'm the head of this tunnel, and therefore I'm the person who gets tunnel.
Yeah, you're absolutely right, Phil. So I'm the head end of this tunnel. I'm the originator of this tunnel, and I have to have full knowledge of load on the network. The second thing that's a problem with our current IP-MPLS networks and why a combination of a centralized view and the distributed routing is critical is that there is zero admission control today available onto the wide area network. The only notion of admission control is on load engineering using historical mechanisms and trying to use past history to predict future performance. Now, it doesn't work very well in the stock market, and it doesn't work very well on networks because we are subject to complete instantaneous, unknowingly caused fluctuations in load on the network. Yes, we can see diurnal patterns, but we don't want to engineer only to diurnal patterns. But why did we ever leave admission control and load admission control out of IP-MPLS? I can't tell you. I've been working on this stuff for 20 years. Why didn't we ever do soft PVCs? I can't tell you. We went all the way to switch virtual circuits and left a couple of the most fundamental building blocks of network engineering and network planning not even on the table.
But and it's interesting. If you go back to the original, the design of the internet protocols, David Clark's paper, he talks about here are the design considerations or goals. And certainly resource accounting is one of them, but it's low down on the list. And so it kind of didn't end up being taken care of very much. But it's really nice. A couple of weeks ago, he gave a guest lecture and went back and revisited these principles and these ideas and kind of they're saying, hey, we never thought about security. Maybe that's something we should have thought of originally. So I think, back when it was starting, didn't seem like a big deal, but now some of those principles which were not, weren't given high priority are now becoming more and more important.
Oh, yeah. And frankly, load-based engineering is one of them. Now, let's talk just a quick trip down history lane. Back in the day, even before there was NSFNet, there was ARPANET. And a lot of my colleagues worked on ARPANET. And what they tried to do was based upon delay or queuing delay across the network, they would fiddle with an IGP metric like OSPF. And if there was high delay, they would give a link worse preference. And if there was low delay, they would give it very high preference, meaning attracting traffic.
Now,
yeah, of course. But you know what, man? That was back in the 80s. And to this day, from that lesson, we have not been able to have an adult conversation between consenting adults even about goddamn load engineering. And look, it's taken, I'll be honest, the next thing that, and I want to get to the next topic, but the next thing we've been working on, of course, is adding useful information into these protocols that are flooding this around the network. So here's where I'm building this up. We just added, here's the shocker, Phil, the delay of a link to be passed with the traffic engineering mechanism, traffic engineering metrics. Here is the utilization of a link. Here is the jitter. In fact, here's some packet loss information that, frankly, we're dropping packets across this link. Now, without getting into the ARPANET war, I said, look, I'm not even trying to create an SPF out of this. I'm not even trying to run a Dijkstra and reroute your traffic. Instead, if you could use this really modern computer science idea of pushing this data out of the network up to a centralized controller, instead of that goddamn protocol SNMP where I need to go poll every device to get the load, and then somehow through some serious machinations match that up with a topology to understand what the load looks like on my network. Hey man, I'm pushing traffic out, I'm pushing this data out in real time. I'm pushing this data out and I see the real-time state of the topology and the utilization and the delay and the packet loss. I now can take that centralized controller and do some really cool shit. And what I can do is place traffic on the network, overcoming best path routing or shortest path routing. And I can fully utilize all the bandwidth that I have deployed, and I can make new protection restoration decisions. But what becomes really interesting is if I know when I want to place load on the network, I can program that load to be placed on the network. Basic stuff. Back up my data center, load my content caches. Here comes an elephant of traffic that I want to send down my network. man, I just can't do this, dialing all the way back, I just can't do this with a head-end view of load engineering onto a network. I can't do this via pulling interfaces to 10,000 or more devices and trying to, create some crazy matrix in the sky. That'll never be real time. Instead, we'll use these modern computer science concepts, and tongue is in my cheek, of push the information out of the network that you want to, have it in a logically centralized place, and in particular, start removing states, because once I have that centralized view and I'm not doing head-end traffic engineering or load engineering, I don't need RSVP. I don't need these protocols. I can do it in a much, much more efficient way. And so these fundamental concepts are really at the forefront of routing protocols, routing technology in the WAN.
This was, as always, the fire hose of fantastically cool information, David. I can't thank you enough. But I think I've taken enough of your time. You've got to go save the internet. So
I got to go do something, that's for sure. But
all right.
hey, if you've got students out there that or other folks that want to get involved in this type of work, we're doing it all in the open. It's all in standards bodies. It's all we're doing quite a bit in open source, and a lot of it is available. Again, I'd like to move the conversation about SDN and orchestration away from, say, just the data center stuff and what you can do with some of these other projects. But routing is still cool, man.
Will do. It is. Cool. Well, have a great night, and thank you again so much.
Hey, talk to you soon, Phil. See you. Bye.